page 628 in your textbook. Okay. Acids and bases, that's what's covered in chapter 14. And chapter 14 is a lot of the basics of acids and bases conceptually and sort of the basics of the math associated with it. Okay? There are two concepts, two definitions of what makes an acid and what makes a base. And the first one is called the Arrhenius concept, and that name should sound familiar. We saw that same scientist's name at the end of chapter 12. Same guy. Okay. Arrhenius defined acids and bases the way that you probably understand it from your Chem 1 classes. Okay. Acids are things that start with hydrogen. They're things that give up hydrogen ions. Bases are compounds that end in hydroxide. Okay? They're things that give up hydroxide ions. That is the original concept of what's an acid, what's a base. It's not that that definition is wrong. It's not wrong. It's just not complete. And really, it's the base part of it that causes issues. As an example, this is a base. Ammonia is a base. And we're going to be dealing with ammonia a lot in the next month. Okay? Ammonia is a base. Do you see hydroxide in its formula? No. The answer is no. There is no OH in there. Okay? But it is a base. So this definition isn't going to work anymore. So this guy, who I believe is Dutch, comes along, Bronsted-Lowry, that's his last name, and tweaks our definition just a little bit. Okay, now before I read it to you, I want to call your attention to something. Okay? A hydrogen ion, I want you to think about what that actually is. How many protons does a hydrogen ion have? One. Hydrogen has no neutrons, and if it has a +1 charge, that means it has lost the only electron that it did have. So folks, a hydrogen ion is nothing more than a proton. Sometimes you will see these things used interchangeably. Okay? Sometimes acids are defined as hydrogen ion donors. Sometimes you'll see them defined as proton donors. Okay? So knowing that, Bronsted-Lowry keeps the acid definition pretty much the same. Acids are things that give away hydrogen ions, but bases are things that accept hydrogen ions. Okay? He took out this part about the hydroxide. Bases give away hydrogen ions, bases accept them. Okay? So, for example, let's look at this just very simple reaction here. All right? Hydrochloric acid, obviously, it's the acid in this scenario. Okay? And look what's happening to it from left to right. Do you see that it is donating, giving away its hydrogen? Can you see that? Okay. What is accepting that hydrogen? H2O. So guess what? In this situation, water is serving as our base because it is accepting that hydrogen. Do any of you know the name of that polyatomic ion? It's not on your list that I gave you at the beginning of the year. And don't call it waterite. Someone always does. It is called hydronium. Write it down. That is an ion we are going to see over and over and over and over again. Hydronium. H3O+. Okay. Let's talk a little vocabulary here. First of all, guys, I hope you realize there is no element A. Okay? There is no element with the symbol A. If I ever write this, what I am trying to say is this is any random acid, just some acid X or whatever. Okay? And if you look, it's very similar to the equation on the previous slide. My acid here is giving up its hydrogen. The H2O is accepting that hydrogen. Okay? Acid, base, here are some new terms for you. A conjugate base is what your acid turns into after it gives away its hydrogen. Let me say that again. When your acid on the reactant side gives away that hydrogen, whatever is left of it is called the conjugate base. Your conjugate acid then is what your base on the reactant side turns into after it accepts that hydrogen. So, guys, you'll have multiple choice questions as simple as this. They'll give you a reaction and say, you know, which of the following is the conjugate base in this reaction? And then you'll have, you know, choices A, B, C, D, E. And the answer would be A minus on the right-hand side. Conjugate acid, conjugate base. Okay, this is just the same reaction. And if you have the PowerPoint slides, I apologize, there should be a double-headed arrow in this reaction here. What does a double-headed arrow mean?
Equilibrium.
It means we're at equilibrium. Okay, I'm sorry I didn't put that in there. But here's the thing. I want you to look at this reaction and look at it from left to right. Which one of these reactants, which one is from left to right accepting a hydrogen? H2O. Okay, great. Now I want you to look at the reaction from right to left. Tell me which one of these is accepting the hydrogen. A minus. Okay? If I say that something is accepting a hydrogen, is that by definition an acid or a base? Base. Ladies and gentlemen, H2O and A minus, both of those are acting like bases. And remember, we're at equilibrium, so we can look at this reaction in both directions. Both of these things are bases. They want to accept that hydrogen, and they're competing for it. They're fighting over it. And whoever wins determines the direction, the dominant direction of this reaction. If H2O ends up being the stronger base of the two, then this reaction will move more in the forward direction. If A minus ends up being the stronger base, then we'll move more in the reverse direction. How are you supposed to know which base is stronger? Well, we'll get to that later on. Ultimately, it's going to decide or depend on how strong that acid is. We're not going to talk any more about that today. We'll get to that later. Okay. Now, just to make sure that you are clear on something, we just wrapped up Chapter 12, Kinetics. What does a lowercase k in Chapter 12 mean? What is that? The rate constant. What does a capital K in chemistry mean? Equilibrium constant. We have seen a lot of capital Ks this year for equilibrium constant. We've seen KEQ, KC, KP. Now we've got another one. Ka. Anybody want to guess what A stands for? Acid. But here's the thing. Guys, a K is a K is a K is a K. Equilibrium constants, no matter what the little letter is, they're all the same thing. What do brackets mean? molarities. Molarity of products over reactants. The only reason that A is there is because this reaction is an acid reaction. Okay? But all equilibrium constants are expressed the same way. Products over reactants. Can you tell me why? Why isn't water in the denominator down here? It's a liquid. What other things are excluded from equilibrium expressions? Solids. Solids and liquids. Okay. Now, let me just explain to you what this one on the right-hand side, what that is. Okay. Since water will be excluded, a lot of people, and you don't have to do this, by the way, this is a choice. A lot of people will, instead of writing the reaction out in full like this, they'll rewrite it like this. Since water won't be included anyway, they write it like that. It's not a different reaction, guys. It's a shorthand way to write this same reaction. And if you write your reaction the shorthand way, then this is what your equilibrium expression looks like. It's a choice. I am going to write them out the long way, but if as you go on and you're getting more comfortable with this material, you might choose to start going the shorthand way, and that's totally fine. I just want to make sure that you understand H3O plus and H plus represent the same thing. It doesn't matter to me or the AP exam, they don't care which way you choose to do it. It's your choice. Now, let's remember our 6 strong acids. Imagine a perfectly clear, breezy summer night. If you haven't thought about which acids are strong in a while, you need to start thinking about it again. Okay? Let's review a little bit here. What makes a strong acid a strong acid? I mean, strong doesn't mean those are the dangerous acids and your weak acids are totally harmless. That's not what that means. Strong means acids that when you put them in water completely dissociate, completely break apart. Give me an example. Give me one of the 6 strong acids. Pick one. Yeah. Okay? Hydrobromin. Sounds good. That's a strong acid. When you put it in water, you will get complete dissociation. Okay? HBr is not going to stay together. It is, all of those HBRs are going to break apart. That's what being a strong acid means. Okay? Same thing. Same thing. All of them do that. Okay? That means, if we were looking at that equation that we had a couple of slides back, the acid plus water, okay? For strong acids, acid is your reactant, we are dominantly moving in the forward direction. Because those acids are breaking apart into their pieces. We're getting lots and lots of product. Okay? I'll talk about this in just a minute. And here's the thing. Some of you, I'm going to write something up on the slide that some of you will have seen before and some of you will not. Okay? Does this equation look familiar to any of you? It's okay if it doesn't. Some of you will have seen it, some of you will not. This is the quickest, easiest way to calculate pH. Okay? And here's the thing. Let's say we're dealing with a strong acid. Let's say we're dealing with HCl. And I hand you a bottle of HCl, and I tell you that it has a molarity of 6. And I say to you, tell me what the pH is of that acid in the bottle. If we're talking about strong acids, whatever the molarity is of the acid as a whole, that is also the concentration of the hydrogen ion. And you can take that number and plug it right in and solve. The reason is because all of the HCl's that get put in that bottle all ionize. They all dissociate. That is not the case with weak acids. Okay, but it is for strong acids. Strong acid calculations are really quick and easy. I'll talk about this later on. There are your 6 strong acids. If you've forgotten them, please review them. So what makes an acid weak? It doesn't mean, weak does not mean harmless, okay? Probably the most dangerous acid you can deal with, hydrofluoric, HF, is a weak acid, okay? It doesn't mean harmless. Weak acid means when you put that acid in water, it does not break apart very much. Instead of having our equilibrium dominantly in the forward direction, this time it's dominantly in the reverse, because we're not getting much breakage of that acid. For weak acids, we are going to be given values for that equilibrium constant. And they're very, very small. Okay? And we're going to talk more about that in just a second. Okay? And let's go back to HF. If I give you a bottle of HF, which I would never do because that's extremely dangerous. Okay? That's the one that eats through skin, eats through bone. It's bad news. Okay? If I gave you a bottle of HF that was 6 molar and I said calculate the pH for me, you couldn't just say, oh, well, the H plus concentration must also be 6. It's not. Okay? It's much, 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 much smaller than 6. And we're not going to do this today, but I will show you how to calculate what this value is, because this is what you need to find the pH. Okay? The reason these are not equal is because very few of these split into the ions. Very few. And these are not all of the weak acids. These are just some examples. How do you know if an acid is a weak acid? It's not strong. It's not one of our 6 strong. One I want to point out to you here, this last one, it looks a little strange because hydrogen is not at the beginning of the formula. Okay? But what polyatomic ion is that? Acetate. For whatever reason, acetate often has, if you're going to turn it into an acid, they often put the H at the end. I don't know why. Please don't ask me. This is acetic acid. Okay? Do you know what acetic acid is called in everyday life?
Vinegar.
Vinegar. Okay? This graphic is just showing you the difference between a strong and a weak acid. Strong acids, almost 100% turn into their ions, whereas a weak acid dissociates a little bit, but for the most part stays intact as the whole compound. Okay? And this is the last thing we're going to do today. We're going to do this together. Right? It says, using table 14.2, that is the blue table on page 628 that you have in front of you. Okay? It's got a list of some weak acids, and then it gives their Ka values. Okay? The question says, arrange the following species according to their strength as bases. Well, you tell me, what is our new definition of a base? What does a base do? It accepts a hydrogen ion. Okay. Well, I want you to tell me if H2O accepts a hydrogen ion, what is its new formula? H3O plus, also known as hydronium. If this ion accepts a hydrogen ion, what does it turn into? HClO2. The minus charge is gone because hydrogen ion has a +1 charge. What about this one? H2SO4. This one? NH4 plus, which you know by name as ammonium. And then this last one? HCN. Hydrocyanic acid. Okay, all I have done is taken these bases and turned them into their acids, their conjugate acids. Okay. I want you to look at our list of acids that I've written in yellow. Are any of these in our 6 strong acid list? Yes or no? Yes. Which one? Not HClO2. Sulfuric. That is one of our 6 strong acids. So I'm going to put a number 1 next to it, meaning that is the number 1 strongest acid in this list. Okay. The next one, I'm just going to tell you because you wouldn't know this. Hydronium comes next. Okay. Sulfuric acid is a strong acid. The remaining 3 here, those are weak acids. Hydronium falls on the border between strong acids and weak acids. Okay, it's on that borderline. So that's number 2. Now the remaining 3, we're going to rank these from strongest acid to the weakest by looking in this table. Which of those 3 remaining has the highest Ka value? HClO2. Okay, so that's next in order. Between these 2, which has the larger Ka value? HCN. So NH4 plus is last. It's the weakest acid in this list. Okay? Well, that's all fine and good. That doesn't actually answer our question here. It says put, not the acids, put the bases in order of their strength. Well, I'm going to say something, and I'm going to say it twice because I want to make sure you get it. A very strong acid has a very weak conjugate base. Let me say it again. A very strong acid has a very weak conjugate base, and vice versa. So you tell me, which base in this list is the strongest base? NH3. That's number 1. What's next? Cn minus. And then ClO2. Water. Okay. This answers the question right there. Okay. Now I know it seems weird to think about the fact that water could be a stronger base than something, because you think water's so neutral. How could that be? But it just means this is an incredibly weak base. Okay? If it's weaker than water, it must be really weak. That is where I'm going to stop.